Today we conclude this section of the course concerning series and sequences. After this we're going to have our first midterm and then we're going to move on to three-dimensional space and vectors. To finish today, let's talk about Taylor polynomials. Taylor polynomials are an extension of the idea of the linear approximation from calculus. So they can be used, just like the linear approximation, to get an estimate for the value of a function. By the end of today, we should be able to find the nth degree Taylor polynomial for a function, and we should be able to get an idea of how far away that Taylor polynomial is from the actual value of the function at any point. The Taylor polynomial is very similar to the Taylor series. It's just that whereas the Taylor series was a series, the Taylor polynomial is a polynomial. So instead of adding together infinitely many power functions, we're only allowed to add together a finite number of power functions. So the Taylor polynomial of degree n, centered at A, is what we get by adding up to a power of n, denoted t for Taylor, with a subscript of n is the degree. This is the function that you get by summing from 0 up to n at the maximum. This formula that we had for the Taylor series, the derivative evaluated at the center, divided by the factorial, times x minus the center to the power. Notice I had to change the index to k because the n is traditionally used in this context to represent the degree of the polynomial, to represent the largest power that we are allowing in this sum. Now I want to point out something interesting. You have already seen a Taylor polynomial before. In particular, you have studied the Taylor polynomial of degree 1. If I write out the formula for t sub 1 of x, then I'm summing as k goes from 0 to 1, the kth derivative divided by the kth factorial times the kth power. When k is equal to 0, I get the 0th derivative, or the original function, evaluated at a. Then when k is 1, I get the first derivative, divided by 1 factorial, but 1 factorial is still just 1. Multiply that by x minus a to the first power, and then stop. Since this is the first degree Taylor polynomial, since this is t sub 1, x minus a to the first power is the highest power that we are allowed. Do you recognize this formula on the right for the Taylor polynomial of degree 1? This is the linear approximation to the function f of x located at the point x equals a. It's exactly the same formula for the linear approximation that we had back in Calc 1. The Taylor polynomial is simply an extension of that idea. We give ourselves more powers, we give ourselves a polynomial of a higher degree to achieve a greater accuracy in our approximation. In general, the higher the value of n, the better the approximation becomes. That's the purpose of the Taylor polynomial, to approximate a tricky or difficult function f of x with a much simpler polynomial function. Let's do a quick example and let's find the nth degree Taylor polynomial of the function natural log of x. Let's do this for n equals 1, 2, 3, and 4. So in other words, we're going to find 4 different Taylor polynomials corresponding to the 4 different degrees 1, 2, 3, and 4. The process is extremely similar to when we found the Taylor series for a function at a given center point. It's just that this time we don't have to try and find a general formula for the series so that we can put it into sigma notation. So we're going to need a couple of different quantities. We're going to need the value of the 0th derivative, in other words, the value of the original function with the center plugged in. This time the function is centered at 1, so I'll plug 1 into the function. Natural log of 1 is equal to 0. Then the first derivative of natural log is equal to 1 over x. If I plug the center into that, I get 1 over 1, which is equal to 1. At this moment, we have all the ingredients that we need to fill in the blanks of the first degree Taylor polynomial. The first degree Taylor polynomial, centered at 1, is equal to the 0th derivative, the output of the original function, with 1 plugged in, plus the first derivative with 1 plugged in, times x minus the center. We can include the 0 factorial and the 1 factorial if we like, but since those quantities are equal to 1, they won't have an effect on the value of the formula. So now, if we fill in the blanks of this general formula with the values that we've calculated for the derivatives, this 0th derivative was equal to 0, so that vanishes. The first derivative was equal to 1, so this becomes 1 times x minus 1 to the first power, or just x minus 1 to the first power. So that is the first degree Taylor polynomial, centered at 1 for the function natural log of x. Now, if I wanted to get the second degree Taylor polynomial, I'm going to need information about the second derivative. So if I take the derivative of 1 over x, using the power rule, I get negative 1 over x squared. If I plug 1 into that, then I get negative 1 over 1, which is simply minus 1. Now I have all the ingredients that I need for the second degree Taylor polynomial. It's equal to the first degree Taylor polynomial with 1 extra term tacked on, corresponding to the power 2. And now the second derivative at the center. Let's fill in those blanks. So this is the value of our second degree Taylor polynomial. To find the third degree Taylor polynomial, let's investigate the third derivative. The derivative of the quantity negative 1 over x squared. If I use the power rule here, I get positive 2 over x cubed. Plug the center into that, and we get 2 over 1. So now let's evaluate our third degree Taylor polynomial. Plus the 1 extra term corresponding to now a power of 3, where we have the third derivative with the center plugged in, divided by 3 factorial, x minus 1 to the third power. And the last thing we have is n equals 4, the fourth degree Taylor polynomial, which requires the value of the fourth derivative. So if we plug that information into the formula for the fourth degree Taylor polynomial, we get everything that we had before. X minus 1, negative 1 over 2 factorial, x minus 1 squared, plus 2 over 3 factorial, x minus 1 cubed. Finally, we have the value of the fourth derivative, negative 6, divided by the fourth factorial times the fourth power. Follow-up question. let's use each of the 4 Taylor polynomials that we calculated above to estimate the value of natural log of 1.01, the same way that we estimated values using linear approximation all the way back in Calc 1. And let's see what benefits we reap by including these extra terms with slightly higher powers. So t sub 1, if I plug in the input of 1.01, then that output is simply equal to 1.01 take away 1, so 0.01. That would be the estimate for the value of natural log of 1.01 using the linear approximation using the first degree Taylor polynomial. If I used the second degree Taylor polynomial, then that estimate found by plugging 1.01 into that formula and that works out to be equal to 0.00995. Okay, let's try it with t sub 3. If we plug x equals 1.01 into this function, then my side work says to me that this is equal to 0.00995033333 and so on. It doesn't actually end up with infinitely repeating 3's, but it's 3's for a long time. And with t sub 4, using that formula from the previous page, my side work shows that t sub 4 is equal to 0.00995033083's, and then 3's for quite some time. Okay, now what is the actual value of natural log of 1.01? The actual value of that, found with the calculator, is 0.00995033085, and then 3 and then several digits after that. Now, reviewing the estimates that we got from our Taylor polynomials, by far the most accurate estimate is the one that we got from t sub 4, which is accurate all the way out to this position wherever it is that 8 is living in the digits. And as we increase the number of terms in our Taylor polynomial, our estimates are just going to get better and better and better. One of the neat things about the Taylor polynomial is that it's just a partial sum of the Taylor series. So if you already know the Taylor series for a function, either because you have already calculated it by hand, or because you got it as a result of manipulating the Taylor series for some primitive function such as sine, cosine, or e to the x, then you can use the Taylor series and just truncate it to get the Taylor polynomial. So for example, find the nth Taylor polynomial centered at 0 of the function sine of x for n equals 1, 3, 5, 7. Then let's go ahead and let's compare the graphs of each of these polynomials to the graph of the function sine. Now we already know, and if you're a math major, you have memorized the fact that sine of x is equal to the sum, as k goes from 0 to infinity, of negative 1 to the k, x to the 2k plus 1, divided by 2k plus 1 factorial. So let's write out a couple of terms of this series, and let's make sure that we stop writing terms when n is equal to 1 for the first degree Taylor polynomial. Okay, so the very first term in this series, corresponding to k equals 0, is negative 1 to the 0, positive 1, x to the power 1, divided by 1 factorial. And I need to stop writing terms right there because this is a degree 1 polynomial. If I included any higher powers of x, this would no longer be a degree 1 polynomial. For t sub 3, we can do the same thing, except we're going to stop writing terms of the series once we get to a term of power 3. So when k was 0, we got the term x. When k is equal to 1, we get negative 1 to the power 1 minus x to the power 2 times 1 plus 1, x to the third power, divided by 2 times 1 plus 1, 3 factorial. So that's x to the power 3, and that's our degree, so we're not going to write any more terms. T sub 5, however, we get to go all the way up to a fifth power. So we have the terms from before, and if we keep writing the series, the next quantity in the series would correspond to k equals 2. So negative 1 to the second power is positive. Then we have x to the power 2 times 2 plus 1, x to the power 5, divided by the matching factorial, 5 factorial. That's a fifth power, so we're going to stop. And then t sub 7 continues in this general pattern, alternating from positive to negative. Then x to the 7th power dividing by the matching factorial. So here I am on Desmos, and let's go ahead and let's compare the graph of sine of x with a variety of different Taylor polynomial approximations to sine of x. Sine of x itself is the graph in red, and it's of course this wavy sinusoidal graph. Whereas the first degree Taylor polynomial equal to just x is this linear equation going through the origin, 0, 0. Now we can see from the graph that sine of x equals x is a pretty good approximation when the x value, when the angle is pretty close to 0. This leads us to a very famous physics/engineering technique that's sometimes referred to as the law of small angles. The law of small angles says that if x is pretty close to 0, then you can basically pull the sine off of sine x and approximate that value using x itself. Future Sam, please play that clip from the Andrew Dotson video.
Hey, how's your physics research coming along? The stupid sign of the function is what's giving me all this trouble, and I'm done staring at it for now. I will try again later. Do you want to go make fun of engineers or something?
Well, I'm the mathematician. Maybe I should take a stab at solving that differential equation for him. He'd be so happy. I should do it.
That's it. I got it. Now he's gonna see how useful it is to have a mathematician as a friend.
Tomorrow.
Andrew, I know I said I was exhausted yesterday and I couldn't hang out, but I saw how that differential equation was getting to you, so I spent a few hours on it, actually several hours on it, and I solved it exactly. The answer is 7. Thank you very much for that. You don't really seem that excited. This solves your problem. You know what? You're absolutely right. I really appreciate it. Wait. That sign of the function. Did you assume small? I assumed small angles, okay? I got an approximate solution. I got 6.999 10 minutes after you left. I'm sorry.
Now, this approximation is pretty good in the vicinity of 0, but as soon as you start to stray beyond maybe x equals -1, x equals +1, the linear equation x and the sinusoidal function sine of x begin to deviate quite dramatically. So let's graph the third degree Taylor polynomial approximation to sine of x. This is the graph in green, the cubic function here, and notice how much more closely and for how much longer This Taylor polynomial approximates sine of x. It actually is holding on pretty strong until about this turning point right here, a little past x equals -1 it looks like, and symmetrically here on the right hand side as well. Now if we go up to the 5th degree Taylor polynomial, this is the graph in purple, and we can say that the graph in purple sticks to the red sinusoidal graph for even longer than the green graph. The deviation from sine of x seems to be occurring at approximately this x-intercept right here. This is where it starts to get really bad. But even that can be remedied by going up to the 7th degree polynomial, which is the graph in black. The graph in black, the 7th degree Taylor polynomial, sticks very close to the red graph for an even longer period of time. So the question becomes, do we have any way to calculate the worst case scenario for the error between our Taylor polynomial and the actual function? We have seen from the graph and from our examples that the difference between our approximation and the function's actual value depends on a couple of different factors. The first thing that it depends on is the distance between the x value and the center. As the value of x gets further and further away from the center, we saw that the value of the Taylor polynomial gets further away from the function's actual value, giving you a larger error. The value of the error also depends on the value of n, on the degree of the Taylor polynomial that you're using for the approximation. As you take a Taylor polynomial with a higher degree, we saw that the error generally decreases, and the approximation is closer to the function's actual value. But the error will also depend in part upon the nature of the function f of x itself. For example, let's compare the Taylor polynomial approximation of the function sine of x to the function 3 sine 2x. Now, these two graphs have exactly the same scale, but notice that the 7th degree Taylor polynomial remains much closer to sine of x for a much longer period of time than if I had 3 sine 2x. This one remains a good approximation until about x equals -3. Versus basically half that, x equals -1.5. So in order to determine the worst case error, accounting for all those different factors, we have the following theorem, which is called the Taylor remainder theorem. Sometimes this is also called Taylor's inequality. We have some function f of x, and we have its nth degree Taylor polynomial, t sub n of x, centered at a. Now suppose that if I took the n plus 1 derivative of the function x, that number, that output is always squeezed between, at the lowest, -m, at the highest, +m in value. For all the values of x in some interval centered at a that we are considering in our application. In that case, difference between the function's actual output value and the approximated value using the nth degree polynomial, the error, cannot be any worse than the following quantity. It can't be any worse than first this number m, which bounds the n plus first derivative, divided by n plus 1 factorial times the absolute value of x minus the center to the power n plus 1. So some things to observe about this inequality. The fact that we are dividing by n plus 1 factorial, this quantity n plus 1 factorial increases very rapidly as n increases. And so we're dividing by it, and that is what's giving us the fact that as n goes up, error goes down. The fact that we are multiplying by the difference between x minus a is the part of the inequality that captures that as x gets further from a, the error goes up. And this number m, which is bounding the derivative, this number m is what captures the unique nature of the function itself. It's what's capturing the difference between a function like sine of x and that function 3 sine of 2x that we had in our other graph. It captures the difference between those two functions. Now in practice, to actually make use of this theorem in any particular application, there can only be one unknown quantity in that given inequality in the theorem, which means that you need at least two. Generally speaking, you're going to have exactly two of the following three pieces of information. And then you can use those to figure out the missing third piece of information. You may be told the maximum distance that you are allowing in your particular problem between the value of x and the center A. So this is going to give you the maximum value of the quantity absolute value of x minus a in the theorem. The second thing that you may know, the second piece of information that's essential for using the Taylor remainder theorem, is the degree of the polynomial that you're using for your approximation, the value of n. And the third thing that you may know at the start, or that you may be trying to figure out, is the worst case scenario for the error. In other words, the worst possible value, the largest possible value, of the absolute value of f of x minus t sub n of x. So let's consider answering some of those questions using the particular function f of x equals sine of x. And let's use the Taylor polynomial centered at 0. So the a is 0, and the f of x is sine of x. Now suppose that we are estimating using the third degree Taylor polynomial. So that information is telling us that in part 1, we are using the value n equals 3. The next piece of information that they tell us is that we are only considering the values of x in the interval negative 0.2 to positive 0.2. So the max distance between the x value and the center is at the endpoint of this interval. The max value is equal to 0.02. From the center at a equals 0, you can either go 0.02 units in the positive x direction or in the negative x direction. That's the max distance. So they say, all right, based on that information, what is the worst case error for your estimate? Now the worst case error is given by this upper bound in Taylor's inequality. It's given by m divided by n plus 1 factorial times x minus a to the power n plus 1, where m is the number that bounds the absolute value of the n plus first derivative. Now the nice thing about f of x equals sine of x all of its derivatives are equal to plus or minus sine plus or minus cosine. And plus or minus sine, plus or minus cosine, all of those quantities are bounded below 1 in absolute value. No matter what derivative you take, the absolute value of that is always going to be less than or equal to 1. Because plus minus sine, plus minus cosine, those functions are always bounded between -1 and 1 in value. So that number 1, which bounds the values of our derivatives, is the number m for this particular application. So having observed all that, let's plug those observations into this expression for the worst case error. The worst case error, m is equal to 1, n plus 1 is equal to 4, so we're dividing by 4 factorial. We have 0.02, and that's being raised to the power n plus 1 equals 4. Now off to the side, I've gone ahead and I've calculated this value, and this turns out to be equal to exactly 6.66 repeating times 10 to the minus 9. Future Sam, please play the clip from The Mummy Returns about this place is cursed.
What is it with you and curses?
Quite a small error, which is fantastic considering that we only have to use the third-degree Taylor polynomial. But the error is so small because the distance between x and the center that we are allowing is extremely small. We're only allowed to go 0.02 units away from the center. Suppose instead, part number 2, we're still working with the center of 0. We're still working with sine of x, but this time we have a specific error that we need to achieve. We need the error to be less than 0.001 units. We're also estimating with the 5th degree Taylor polynomial. So for what values of x can we actually estimate sine of x using this degree Taylor polynomial with this allowable error? Based on this, our worst case error, which is equal to m divided by n plus 1 factorial x minus a to the n plus 1, cannot exceed 0.001 units. That's the very worst it can be. Now in this problem, our m is still 1 because the function itself hasn't changed. But this time, the value of n is given to us 5. So let's fill in all the blanks that we have. The m for this function is 1, n plus 1 is 6, we have x minus the center at 0, being raised to the power 6, and that's supposed to be 0.01 at the worst. Now if I take this equation and I go about solving it for x, the first thing that I'm going to do is multiply by 6 factorial, 0.001 times 6 factorial, and then to isolate absolute value of x, I'll use the 6th root. So this quantity in the calculator works out to be 0.946. If I round down just to be safe, so what does that imply about the allowable values of x? We can either be negative 0.946 or anything up to positive 0.946. For values of x in this particular interval, guaranteed our error will be less than the maximum possible error that we are allowing, 0.001. In part number 3, this time we know that we need the error to be less than 0.01 units, and we need to estimate the value of sine of x for x's in between negative 0.5 and 0.5. So in this case, the question is, what value of n do we need? What degree Taylor polynomial is needed to ensure this level of accuracy? So we're told that the worst case error is going to be 0.01. And we're also told that the max value of the distance between x and the center, well, in this case, our interval is showing us that we can be 0.5 units away from the center at a equals 0, either in the positive or negative directions. We still have this value of m equals positive 1 because we're still working with sine of x. So let's fill in as many blanks as we can. We have worst case error, m equals 1, divided by n plus 1 factorial, times 0.5 to the power n plus 1, that cannot exceed 0.01 at the very worst. Now this particular equation is different from the ones that we had in part 1 and 2. Because in this particular equation, the quantity that we're solving for, the number n, appears inside a quantity that has the factorial applied to it. Which means that there's not really any way to algorithmically solve this equation. When faced with an equation where the unknown is inside a factorial, really the only way to handle a situation like that is to plug in various integers n until the equation / inequality is satisfied. So off to the side, I've gone ahead and I have plugged in whole number values of n for n starting from 0 and increasing until my error is small enough to meet the requirements of the problem. When n was 0, I got an error of 1/2 of a unit, which is way too big. And when n is equal to 1, my error was 0.125, still too large. When n was 2, the error was 0.021, still too large. Finally, when n was 3, the worst case scenario error was 0.003 units, which finally guaranteed that the error would be smaller than the acceptable margin of 0.01 units. So in answer to this question, in order to approximate sine of x to the specified degree of accuracy, for x's in the interval negative 0.5 to 0.5, we would need to use a third degree Taylor polynomial. As a final example, I would like to consider the problem of approximating the cube root function, cube root of x, using the second degree Taylor polynomial centered at 8, for x's which are in the interval from 7 to 9. If we did such a thing, what would be the worst possible error that we could incur with such an approximation? And really what I would like to get at in this problem is the situation of how to deal with this magnitude of the n plus first derivative of the function when the function is not something as simple as sine or cosine or some variation thereof. Now in this problem, what we do know is that we are working with the second degree Taylor polynomial. So n is equal to 2 in this problem, and n plus 1 is equal to 3. So in order to get a read on the value of the number m, what I'm going to do is I'm going to start by calculating the third derivative of the cube root function. So f of x is equal to x to the power 1/3, which means that the first derivative is equal to 1/3 x to the power minus 2/3. So the second derivative is negative 2 over 9 x to the negative 5/3, which makes the third derivative equal to positive 10 over 27 x to the power negative 8 over 3. So let's think about the magnitude of this quantity for x in the interval 7 to 9. In order to get a read on the number which might bound to this function from above, the maximum possible value of this number, I'm going to go ahead and go out to Desmos and graph this function for x's in the interval from 7 to 9. So here I am on Desmos with the graph of the third derivative absolute value for x's in the interval from 7 to 9. So what is the largest that this function could possibly be? The largest value of that function for x's between 7 and 9 is achieved when x is equal to 7. This function is decreasing, so its largest value is achieved when x is as small as possible, when x is equal to 7. The function's value will never exceed what you get when you plug in the smallest possible value of x, namely x equals 7. So that number, 10 over 27 times 7 to the power negative 8 over 3, is the value of m for this particular function. Now that is quite cumbersome, so let's go ahead and get a numerical approximation. 0.00207. Okay, so now having established the value of m that is valid for this function on this interval, let's also note that the values of x in 7 to 9 can get at most 1 unit away from the specified center at x equals 8. Seven and 9 are both 1 unit away from the center at 8. So putting it all together, the worst case error is given by Taylor's inequality, the m, which is 0.00207, divided by n plus 1 factorial, 3 factorial, and then the max distance between x and the center, 1, raised to the power n plus 1, so raised to the power 3. 0.00345. That is the largest possible difference between our approximation using the second degree Taylor polynomial and the function's actual value. Not bad at all. Alright, that concludes not only today's material, but the entire material of the course covering sequences and series. Starting tomorrow and the day after that, we'll be working on the first midterm. To summarize what we did today, we gave the formula for the nth degree Taylor polynomial centered at A, and we practiced finding it first using the direct calculation and then by truncating an already known Taylor series. Then we studied Taylor's remainder theorem and used that to answer various questions about the error in approximating a function's value using the Taylor polynomial.